Hello viewers. So I'll walk through the network I designed, configured and tested in this Cisco packet tracer. The goal of this assignment was to convert the previous RIP based design into a more scalable and secure enterprise network by using OSPF routing and a GRE site-to-site tunnel between Sydney and Melbourne. The final topology delivers full inter-branch communication with stable routing, redundancy through tunneling, and correct LAN segmentation at both sites. So my topology has like two main branch routers, Sydney router and Melbourne router, which is connected by an ISP. Sydney contains two networks, static subnet 172.86.1.0/24 used for the server and admin PCs, and DHCP subnet 172.86.20.0/24 for general employees. And Melbourne contains two VLAN networks, VLAN 10 which is for IT and VLAN 20 for HR. Both branches are connected through a simulated ISP using WAN serial links, and I have added a GRE tunnel O interface which creates a virtual point-to-point link between Sydney router and Melbourne router. So the GRE tunnel was the core requirement of this assignment. On the Sydney router, I configured tunnel O with an IP address. Let me show you the IP address. After I hover here, it would have shown, but I don't know what's wrong. Anyway, on the Sydney router, I configured tunnel O with an IP address 10.10.10.1/30, and on the Melbourne router I configured 10.10.10.2/30. The tunnel source and destination reference the router's WAN interface. Sydney uses 19 192.168.100.1, whereas is the tunnel source, whereas the Melbourne router uses 192.168.200.2 as the tunnel destination. The GRE tunnel allowed the two routers to form OSPF adjacency and act as if they are directly connected, even though the real path is via ISP. OSPF routing implementations. I replaced RIP with OSPF because OSPF is more faster, more scalable, and supports routing over GRE tunnels. So now you can see the IP address as I mentioned earlier. So yeah, I was saying that I enabled OSPF process 1 on both routers and advertised all LAN networks, all WAN networks, and the tunnel 0 network. All interfaces were placed in area 0, which keeps the OSPF design simple and fully standard compliant. And after configuration, the routers formed a full OSPF adjacency, which I verified using the command show IP OSPF neighbor. This ensures that both routers exchange routes reliably and can dynamically update paths if links changed, and so I'll walk through the Melbourne VLAN design. For the Melbourne, I created a VLAN 10 for IT users, VLAN 20 for HR users. So these two switches are like connected using trunk links, and the router provides inter-VLAN routing. Each PC in Melbourne receives the correct default gateway through the router sub-interfaces, ensuring that VLAN traffic can reach the tunnel and Sydney networks. So basically in Sydney router, I've got one PC. Yeah, so the IP address of this PC you can see here. OC 172. It disappeared. 172.86.1.10/24. So for the testing, we will test it from PC2 to PC3. Okay, so what we'll do is command prompt, and we'll just simply type the IP address. Ping 172.86.1.10. Let's see. So as you can see, we did a ping test, and here we lost like 25% packets, but still. So let's try from PC1 desktop, command prompt, ping 72.10/24. Let's put this slash. Sorry. Ping 172.86.1.10. So that's the IP address for PC3. Let's try. So as you can see, our ping test is 100% successful. So in conclusion, the network now meets all the requirements, and the GRE tunnel ensures secure branch to branch connectivity. OSPF provides fast and scalable routing, and the LANs in both branches operate correctly, like with DHCP and static addressing and VLANs. This design is more modern, secure, and reliable compared to the previous previous RIP based design, and it lays a solid foundation for future expansion. Thank you so much guys for watching this video.